Hello, my name is Cody Newman from iMedisync, and in this video I will be going over connectivity and imaginary coherence. And by the end of this video, it is the goal that you should be able to understand this diagram at the end of the QEEG reports, or any other similar connectivity diagram. So, to start off with, we're going to talk about what is connectivity, why it matters. Then we're going to move on to S. Loretta and the 68 regions of interest. Following that, we'll actually talk about how to calculate coherence, talking about the assumptions that go into the mathematical model, understanding phase, and then the actual solving of the equations. Then we'll give an overview of what the full analysis pipeline looks like, and we'll end with how to actually interpret the results with a few examples referring to regional connectivity, quadrant-based connectivity, and a more macro-scale connectivity, and then some tips on how to use connectivity in general. So let's get started. Why functional connectivity matters. So connectivity is the way in which brain regions communicate, and there's different types of connectivity. While structural connectivity maps the physical connections between areas, functional connectivity shows actively coordinated regions. And for a lot of these, we're going to use the examples of people talking, like the people are the different regions of your brain. So, to understand what the difference is, structural connectivity is like a couple with their hands being held at a party constantly together, whereas the functional connectivity is who's actually communicating with who. So even though two segments might be connected, one of them might actually be communicating with another area, and that's what functional connectivity is. And connectivity like this shines light to the networks responsible for our thoughts, emotions, and actions. Now, I'm going to be using coherence and connectivity kind of interchangeably, but coherence is the actual mathematical method used to quantify the synchronicity of neuronal activity. So it actually gives a numerical output, and that number is what we are using to describe this functional connectivity. Now, imaginary coherence is a subset of coherence, and we'll explain the differences and why we use imaginary coherence for EEG a little bit later. So now let's look at a few examples for why we might want to be using functional connectivity or why it's being used in general. A really popular one is with epilepsy. Functional connectivity is what they use to identify the networks involved in seizure propagation, and that lets the surgeons know where to operate. Altered connectivity has been shown in many studies to be associated with hallucinations that we see with schizophrenia. There's a lot of studies about how in autism spectrum disorders, there's different forms of atypical connectivity between the regions responsible for social cognition. And abnormal connectivity between hemispheres has a wide range of applications, from Alzheimer's, ADHD, to even bipolar disorder. There's a lot of research on how connectivity affects these things. So, next, we're going to actually talk about the 68 regions of interest and S. Loretta, so that way we understand what regions we're talking about with this connectivity. So what are the 68 regions of interest, or ROIs? So this is a long list. There's 34 items here because this is the left hemisphere, and then with both hemispheres, we get a total of 68. And they are based on the Desikin-Killeney Atlas. This was made by manual MRI labeling of 40 diverse brains. So experts trace the regions based on their curvature, landmarks. They use atlases and neuroanatomists, and then refine those labels using the different features of the brains that they were analyzing. Then they tied each one of these regions of interest to a specific gyrus or region. So these are a few examples of different regions of interest. So we have these different regions, all of which are connected in different ways and are utilized and connected to different aspects of the brain as a whole. But how do we actually measure them? And how are we going to measure them from EEG? Because we actually face what is called an undetermined system. We have 68 things we're trying to label, but in our case, only 19 electrode channels. But the thing to remember here is we don't just have the data at these channels. Because we're using the 1020 system, we also have 3D coordinates in space for each one of these channels. So then by combining the spatial information for where the electrode should be and the temporal data, we can actually mathematically estimate the source of brain activity. Now, I won't go too in depth on this actual algorithm for source localization, but I think this is a really good way of visualizing it, which is, let's say you have 3 people talking and only 2 microphones. We have our red, blue, and green person. Now, those microphones are mixing all of those voices up into some kind of jarbled mess. But using this algorithm, knowing that, for example, microphone A is close to red and blue and far from green, we can actually extract meaningful data and get back, in theory, the initial sources we started with. So when we're using these source localization algorithms, we still have an ill-posed mathematical model. So we have to make some assumptions. The first assumption is that we're going to assume minimum norm estimates. We're assuming that the brain is an efficient organ, which it is, and it's using the smallest overall activity to explain the data. So this is like saying, rather than assume that 2 voices are yelling from a mile away, we'll assume that they're whispering right next to the microphone. We're also going to be using dipoles. A dipole is just a way of modeling that when there's some sort of large firing of neurons, there's going to be a positive charge in one direction, which is in our little cases here where the arrow is pointing, and there's going to be a negative charge in the opposite direction. And we're going to also kind of pay attention to the orientation of these different dipoles. Because let's imagine a dipole on the surface, but it's tangential. It's kind of flat with the head pointing forward. The EEG right above it is only going to read a pretty small signal because it's not being directed at it. The dipole is not pointing at the electrode. Whereas if the dipole is pointing outwards towards the electrodes, we're going to get a much larger signal. So these algorithms are going to prefer these radially faced sources over ones that might be facing internally. So once we have these kind of dipoles where we're estimating the sounds are coming from, we can actually predict what the EEG signature would be at all these different regions in the brain. So what we do is we end up with thousands of what are called voxels, which are like the 3D pixels, and we actually know what the EEG is at each one of these voxels. And then we can just average an entire region, all the voxels in that region, and get an idea of what the EEG would look at one of these 68 regions of interest. So this algorithm is good, but it's not perfect. Some things to keep in mind is that we are dealing with estimates, not direct measurements, unless the EEG is implanted in the brain. So the accuracy here is going to depend on the quality of the EEG data, the head model being used, and how valid those assumptions we made are. And spatial resolution is going to be limited with only 19 electrodes, so the estimates are going to be coarser than with some sort of high-density EEG, but we still get biologically meaningful approximations. Wynn Dance et al. Actually found that these 19-channel EEG recordings did not reduce the accuracy when performing this source localization procedure compared to MEG, MRI, or 128-channel EEG recordings. So now that we have an idea of how we can get the EEG at these different 68 regions of interest, let's actually talk about how to calculate coherence between the regions, starting off with some assumptions. These are the 3 assumptions we're going to talk about: linearity, stationarity, and volume conduction is instantaneous. So, assumption number 1, linearity, simple and expected responses. We're just assuming that the system is linear, which means that the conversation for our metaphor here must be basic and predictable. I say hi, you say hello. I say hi, you say hello. Repeat, repeat, repeat. But in reality, of course, the brain is not linear. So this is going to be lowering our accuracy. You know, people are shouting, rambling, interrupting. The conversations can definitely vary, but we're not going to be able to understand or at least analyze those very different versions of connectivity. So an example of a time where this assumption kind of fails or where connectivity measurement might not work is with the transient synchronization between the tempoparietal junction and the frontal eye fields during a rapid shift of visual attention. So maybe during an eyes open recording, I notice something out of the corner of my eye, but really quickly snap back to focusing loosely in front of myself. Now, these linear measures like coherence are going to miss this fleeting nonlinear interaction because we're averaging over such a large time period, so we'll lose anything that's not linear like we expect. So then assumption number 2 is stationarity. This is assuming that these sources are repetitive and not moving. They have a constant frequency and amplitude over time. So in our metaphor, people are repeating themselves and standing still. Of course, this isn't accurate, and brain regions and networks are constantly evolving their path and shape, and even the regions being used for the networks. So, a really good example of this is what if a patient is drowsy? If a client's drowsy in the chair, and maybe they shift into a stage 1 of sleep, which is bound to happen sometimes, we're going to see major changes in the EEG signature. For one, their theta, which should be low in a resting state EEG recording, might become really dominant in the frontal lobe of their brain in that stage 1 sleep, which is like movement within the brain. That's going to break our stationarity assumption, and when we calculate coherence, we're going to average all of that out, and we're not going to get any meaningful results. So that's assumption 2, and assumption 3 is that volume conduction is instantaneous. So this one's a little more complex, but basically we're just saying that all electrodes are picking up the same signals at the same time, regardless of how far away they are to the source. So with our little conversation metaphor, we're saying these microphones ignore the speed of sound. Even though you might have one on one side of the room, one on the opposite, we're going to assume that if you're hearing one person, they're going to be perfectly in sync with each other. So that means in our brain case that if 2 electrodes are reading the same wave pattern perfectly in sync, it's more likely than not that they're just picking up data from one singular source, not that they're picking up data from 2 separate sources that are just perfectly in sync with one another. And that's because what we read on the electrodes is passive volume conduction. So we're just reading electricity kind of loosely flowing between the source and our scalp. Whereas these conversations between different areas of the brain, they actually are using neuronal pathways, which take a lot longer to communicate from one area to the next. So because of that, we're going to just assume that whenever we have a single source, that all the electrodes pick it up at the same time. And we'll touch on this assumption a little bit later when it becomes relevant. So those are our 3 assumptions for coherence measurements. And as long as these 3 are met and we know what we're looking for, we can start to actually calculate imaginary coherence. So to start off with, we're going to give a little bit of background on phase and the complex plane. So what do we have here? We have kind of EEG signal. We have 68 of these signals after our S-Loretta analysis at all of these different regions of interest. What we're going to do after we have those different signals is break them down into separate epochs of approximately 1/3 of a second. Some epochs might be around 2 seconds. That kind of varies in the literature. And then we're going to take each one of these epochs and we're going to split it into its specific frequency groups using a Fourier transform. We're not going to talk about the details of the Fourier transform today, but just know we're trying to take out how much beta is there, how much alpha, how much gamma, etc., and separate those into different signals. So with that whole breakdown, we're taking a bunch of data and we're going to be splitting it, in our case, into 68 of these different signals, each broken up into maybe thousands of epochs. And then each epoch for each signal is broken up into alpha, beta, gamma, etc. So all we have are clean waves in one frequency for a small period of time. So now let's break down these waves and talk about some of the dynamics and variables associated with them. There's 3 that we really care about. There's the frequency. This is the speed of the wave. So again, that might be like alpha, beta, gamma for our uses. Amplitude, the power of the wave. And then this phase, which is kind of like the start time or the value at time equals 0. As the frequency stays the same and the amplitude stays the same, you can see how the phase might actually shift. And that's what we're going to be using to measure, are these signals really in sync if they have similar phase? So in order to do this analysis, we need to convert our waves into the complex plane that you can see in the bottom right. A good way of thinking of this is, instead of imagining our wave in 2D space, let's imagine a spring. And just like a spring, we still have a frequency, we still have an amplitude, and we still have a phase. You can see how as the spring moves, we still have this kind of undulating valleys and hills after each other. But what we can do now that we have this spring visualization is look at it head on. And notice here that we still have a lot of the same variables. We still have our frequency, the speed that the spring is moving. We can still see the amplitude, because that's just the height of the spring from the center. And most importantly, we have a really good view now of the phase of that start point of the spring. And what we do with this sort of model is move it into the imaginary or complex plane. This is just like any other coordinate system where you have horizontal and vertical and you can plot points on it. We just happen to be using the imaginary numbers as our vertical axis and real numbers as the horizontal axis. What is an imaginary number? It's not super relevant. Technically, it's this variable or value I, which is equal to the square root of -1, and it's just used by mathematicians to help convert time signals into frequency analysis. But we don't need to really pay attention to that. All we need to know is that now we can actually plot data on this complex plane and still find out the phase and the amplitude from it. But one thing you may notice is when we just plot a single point, we're losing that frequency, the speed that that thing was rotating at. And that's why for coherence, we're only going to compare specific frequencies. We're never mixing different frequencies because different frequencies can never be coherent. So if we imagine our two little phase diagrams spinning at two different speeds, notice that the distance between them, the angle between them, is constantly changing. And we don't want that because that means that they're not in sync. And they can never really be in sync in this situation, which is why we don't care about frequency. And what really matters here is the phase and the amplitude. So now that we have a basic idea of what this complex plane is, let's see how we can use it to compare two waves. So, step 1, we're breaking down the two waves being compared, channel A and channel B. We're going to find one single epoch and extract it from the data, the same time point for both. Then we do our Fourier analysis to extract, for our examples here, we're going to say alpha waves. And then we convert that wave into the imaginary plane. We still get the phase, we still get the amplitude, and we know they're both alpha, so we don't really care about what the frequency is. Now we have these two waves on this little circular diagram. Again, think of this as the horizontal spring. And even if one has an amplitude much larger than the other, they're still going at the same frequency. So they'll still line up nicely and hypothetically have a very consistent phase between them. So we plot those on the imaginary axis, and we can drop those circles because all we really care about and all the information we need comes from those singular points. So now that we have our two waves visualized in this complex plane, we can combine them to get this combined wave. There's going to be two steps here. One is multiply their amplitudes. So how long these lines are, the amplitudes of those waves. Note here that if one is really small, if we don't have a lot of alpha in one channel, our combined wave is going to be really small. And if one or both of them have a lot of alpha, our combined wave is going to be really big. So the more alpha in this case there is in both of these channels, the higher this amplitude of this combined wave will be. Next, we're going to find the difference in their phase. So the phase is just that angle. We're saying the angle from the real axis. You can see this P1 is pretty large. P2 is about half of it. And all we need to do is find the difference to get the new phase of our new combined wave. So we write that as phase 1 minus phase 2. And what you can note here is that if their phases were really similar, if we had almost equal phase 1 and phase 2, that combined wave phase is going to be really small. So that small phase is going to correspond to really in sync frequencies. So now what we have is an amplitude and a phase, and we can take that information and plot it again on that complex plane. And that's what we're calling cross-spectrum analysis. Some fancy math is happening behind the scenes, but that's the basic idea. So now we've figured out how to get that combined wave for a single epoch. We just need to do that now for all the epochs. So you can imagine there may be thousands of these different combined waves. And once we have all of those different combined waves for all the epochs in the entire recording, we can average them to get us an average direction. And then we normalize them, which is basically just making sure that the resulting value is between 0 and 1. Because we don't know what 120 means in this context, but what we do know now is that 1 is the maximum and 0 is the minimum. And that gives us our averaged and normalized result. So how can we actually interpret this new wave combined vector? So the amplitude is an average measure of how strong, in our example, the alpha frequencies were for all the epochs. So the closer it is to 1, the longer that line is, the more alpha was within both of these channels at the same time. So the larger it is, again, the more alpha there will be. And then the phase of this new combined wave is an average measure for how similar in phase all these epochs were all averaged together. So the closer that phase is to 0, so the smaller that angle is from the real axis, the more identical the phase relationships were between the channels. So let's focus on that part. The closer it is to 0, the more identical the phase relationship was between the channels. So does that mean that 0 is perfect? No. We're going to go back now to that instantaneous volume conduction assumption. A perfect phase relationship is impossible because of this assumption of instantaneous volume conduction. If two signals are perfectly in sync, more likely it means that they're both reading the exact same signal, not two regions talking to each other. But if they have some phase shift between them, then they might be two connected regions. So let's look at this a little closer. Let's say we have two electrodes, one in the front of the head, one in the back of the head, and they're reading an identical wave. What that means is most likely we're reading a wave from a single location in the brain that is being picked up by both electrodes. Now compare that to if the signals are slightly offset from each other. One's a little bit slower or faster, and they're not perfectly in sync. Now we actually have a situation where it might actually be two different regions that are synchronized with each other, but not perfectly synchronized, because that just isn't possible with our assumptions. So how do we do that in reality? Is we remove the real component. So we have two signals with really consistent phase, so it's still consistent, but it's far away from 0, and that amplitude is much greater than 0. When we ignore the real component and just look at the imaginary axis, we have high imaginary coherence. It doesn't matter if it's positive or negative, the outcome is the same, it's large coherence. Now, if we have two signals that still have a lot of the same amplitude or a lot of the same frequency, so maybe a lot of alpha, but they're perfectly consistent in phase, when we remove that real component and look at where it lines up with the imaginary axis, we end up with low imaginary coherence. So in that situation, we wouldn't get high connectivity. And then if you just imagine two signals that aren't really in sync and they don't have a lot of the same frequency, again, we're going to get that same low imaginary coherence. So what happens by using only the imaginary component of coherence is we get signals that have some sort of phase relationship, that have a lot of the same signal, and that aren't perfectly in sync with one another, because that's impossible. So let's put all of that together. That was a lot to go through pretty quickly. So we start off with our EEG, any 19-channel EEG. We do our source localization. So we use our S-Loretta analysis to know what the EEG looks like at all these different voxels throughout the brain. We average those voxels, in our case, for these 68 regions of interest. So maybe that purple region, when averaged together, gets a wave that looks like that. Then we break the signal down for all 68 of these regions of interest into different epochs, and for each epoch into its specific frequency bands. Then we calculate the coherence between these. So we plot them in the imaginary plane, or the complex plane. We average all the epochs together, giving us some value. We move that value to the imaginary axis, and then that number, how far away it is from the origin, is our value of coherence. Then we can do that for all the possible combinations, region 1 to region 2, region 1 to region 3, region 3 to region 64. All those different combinations will give us a different coherence value, or imaginary coherence value. And lastly, we can visualize these values in something that looks like this. So now that we know how to get this diagram, what is actually on it? Well, to start with, we have the frequency band. Remember, these connectivity analyses can only be for a specific frequency band, not combinations. Each one of these little phrases around the outside of the circle is a different one of these regions of interest. The colors next to these regions of interest are actually the source localization values, so the power in this frequency band at each of those locations. And then the meat and potatoes here is this connectivity diagram in the middle, where red areas are hyperconnected, meaning that there's larger than average, a statistically larger than average amount of connectivity between those regions, and blue is hypoconnected. So there's a statistically less connectivity between those regions than a normal database would show. Or if we're not using a database, just below some threshold that we set. And that's how you get this diagram here. So now that we know how to calculate connectivity and how to read a connectivity chart, now we can start to look at how to interpret the results from these analyses. And there's different levels of analysis that we're going to talk about here. We can start with the real nitty-gritty with region-to-region pathways. So focused analysis on very specific anatomical connections that have been studied in the literature and what their symptom correlates are. So really looking at maybe one line in particular in that connectivity diagram. We can also look at entire networks when we're talking about connectivity. So rather than focus on the entire brain, just focus on the regions that are relevant for a specific network to see how that network is functioning. We can compare interhemispheric or intrahemispheric connectivity, and this is a good way of measuring the symmetry or asymmetry of the brain. And we can look at a global excess or deficit in frequency-specific connectivity to look for more large-scale network dysregulation. And now let's talk about some examples of each of these. So to start with region-to-region connectivity. So this can really help us understand the neural underpinnings of various symptoms and disorders, as long as we know what all of these different regions of interest do. So some examples: atypical connectivity in the gamma band in language-related areas such as the temporoparietal junction or the inferior frontal gyrus has been observed in individuals with autism. In schizophrenia, we might also see altered gamma connectivity in the memory regions, such as the parahippocampal gyrus. And some studies have found that reduced integrity in the connections of the arcuate fasciculus has been found in individuals with language impairments. So that's the region to region. We're talking about very specific areas, what they do, and then how that altered connectivity might be affecting the brain. Next, we'll zoom out and just look at specific networks. So for example, this diagram here is only looking at the regions associated with the default mode network, specifically in the alpha 2 band. So the default mode network is active during rest and deactivated during task performance. So for a resting state EEG, we do expect to see this network functioning. And some studies have found altered asymmetry in this network in schizophrenia. And this is used a lot to know how different interventions might be affecting the brain and can be really good for seeing pre and post how well treatment is working. And specifically, we're generally looking at the alpha and beta bands because we're talking about a resting state network. So if you're doing sleep analysis, you might be looking at the slower bands like theta if we're talking about drowsiness. Or if we're talking about active tasks, we might want to look at those networks being used in the attention mode network, which would be mostly in the beta bands. So now zooming out one more time. Now we can talk about interhemispheric asymmetric brain connectivity. So this diagram at the bottom is showing us the connectivity in a 3D brain map and then judging by hemisphere how well those hemispheres of the brain are connected. So the way we do this generally is by summing the amount of hypercoherent connections minus the amount of hypocoherent connections. So if we look at this diagram, especially on the top view at the very bottom, you can see a lot of these hypoconnections in the left hemisphere. So connections that are not as strong as we would expect them to be. And because of that, the left hemisphere you can see is showing weaker connectivity compared to the right. And this is a way that we can measure the symmetry or asymmetry of the brain. Generally, frequency selection when you're doing this sort of analysis varies. So if we're talking about language functions, we might be talking in things like theta or gamma, or again, if we're talking about default mode network functions, we might be looking at the alpha and beta bands. So still talking about this asymmetry, all sorts of cognitive functions actually rely on some asymmetry, but certain ones have been correlated to certain disorders. So Alzheimer's disease generally has a loss of connections in the left hemisphere. Schizophrenia has shown reduced right hand asymmetry, at least less efficiency in that right hand networks. Autism usually has atypical asymmetries in those language related pathways as we mentioned, and generally a reduced rightward asymmetry, so a weaker right hemisphere than left. And ADHD can be related to reduced asymmetry on the right brain and improved or overactive left hemisphere network efficiency. And even bipolar disorder, you can see altered left-right asymmetry. Specifically, this has been found in the white matter tracts, and that may be why there is this mood dysregulation. So then lastly, zooming out one more time, if we're looking at the full connectivity of the brain, there are different things we can find from this too. So for autism spectrum disorder, we do find a lot of beta band and theta band hyperconnectivity generally. And this has been used to classify children with autism with a really high degree of success. Schizophrenia, generally you'll see altered global connectivity in all frequency bands. Alzheimer's disease, a lot of times we'll again see weakened connectivity in all of the networks, so a lot of hypoconnections in all of the different frequency bands. So those are just some examples of how you might actually look at a chart like this, and when you're looking through the research or when you're looking at a patient-specific lived experience, this is how you can kind of think of those different levels and figure out how deep you need to get to understand the connectivity of their brain. So to end, we're going to give some analysis tips, putting everything together and helping you actually use connectivity in your EEG analyses. So the big one here, S-Loretta and connectivity relies on clean EEG signals. You need to have good data in to get good data out. Now, how long should a recording be? Generally, the research is actually on the shorter end, in the 2 to 10 minute range, because the longer it is, on the plus side, we'll have more luck finding connected regions, because as long as they're communicating regularly, that'll start to get stronger and stronger the longer you go. But as we mentioned, any changes in state, so if they're getting drowsy, falling asleep, or any other possible state changes that could happen during a resting state EEG, it'll break our assumption of stationarity and will lead to inaccurate results. So that's why generally you're doing connectivity on the shorter scale. We usually recommend around 5 minutes of eyes closed resting state EEG for the most accurate results. Eyes open or eyes closed. As I said, eyes closed is generally what we recommend, and that's because most of the research is focused on eyes closed data, and there is also research showing that the connectivity does change depending on eyes open or eyes closed. So choose wisely and be aware that by analyzing an eyes open connectivity EEG, it might not match what you'd expect to see in a resting state. How many channels do you need? If you have adequate spatial resolution, so the entire head has electrodes somewhere, you're generally going to get the same results. Research has found no significant differences in these voxel analyses on EEGs done with 19 channels versus 128 channels. But if you're only doing maybe a 3-channel EEG, you don't have that spatial resolution, and you're not going to be able to get a full picture. When you're doing this sort of analysis, I recommend starting at the macro level before getting into those specific regional details. It's a lot easier to start by saying, wow, they have a lot of hypercoherent beta in their brain. What does that mean? Before you start looking at the nitty-gritty and trying to figure out why there's a hypoconnection between the parahippocampal and the arcuate facilis. You can start at the larger level and work your way towards that deeper analysis. Read the literature. There's so many connectivity studies done out there, not just with EEG, but also MRI and MEG, and those results still are accurate when you're looking at an EEG. You're not always going to see the exact same results. For example, when you're doing MEG, some of the assumptions do change, so you get different forms of dipoles, but we still think that the literature generally holds up regardless of what the analysis is you're doing, and it's the easiest way to start to really understand these connectivity diagrams. When you're trying to figure out what frequency band to look at, focus on the frequency band that's related with the functional regions you are analyzing. So if you're looking at a resting state default mode network, beta and alpha are the frequency bands you're focusing on. Whereas if you're doing language processing, theta or gamma may be more informative. And then how do I know what brain regions are within the different regions of interest, these 68 regions of interest that we focus on? Because sometimes you're going to see something in the literature and it's going to be talking about a region that's not actually one of these 68 regions of interest, because different atlases use different definitions of what these parts of the brains are. So one thing you can use, a free tool, is called FreeSurfer. It's developed by Harvard, and if you can get it running, it's really nice. It lets you click on any region. It'll tell you all the different terms for that region. Specifically, it does have the 68 regions of interest from the Desikin-Kalani Atlas, but it has every definition, really, and this can be really helpful for learning the brain. But if you don't want to get FreeSurfer working, I always recommend Google. There's almost always going to be some study or some atlas or some textbook that's related these regions to each other. So if you just look up which one of the 68 regions of interest are most have the most overlap with maybe this Brodmann area, you'll be able to find the results in no time. So with that, thank you so much for watching, and go out there and do some connectivity analysis.